Hello everyone, welcome to the second class of this course titled Mathematical Foundations of Machine Learning. So in this class I will mostly be dealing with the foundations of probability theory and try to connect the deterministic viewpoint of function approximation to the probabilistic viewpoint of distribution estimation. While doing it, I will define the foundations of probability theory starting from the sample spaces, the sigma algebra, distribution functions and so on. Last time we defined the problem of machine learning as that of function approximation. So we said that you are given observations from two sets and there exists a mapping between them, which we denoted by the letter f, and the task was to estimate the underlying f given observations from these two sets. Now why is that of importance? It is of importance because in lot of practical scenarios we want to predict. So what do you mean by prediction? Given that there exists a function between two sets and I have given some points for which I do not know what the range is from the domain, I want to predict what the range is going to be. So that is of importance in multiple practical scenarios. And one example that we saw the last time was that of having an image and finding out whether that image corresponds to a benign case or a malignant case, right. So you can imagine that there exists a function that maps the image to a set that consists of two values represented by 0 and 1, one corresponding to each label. Now the task is to find out the underlying function, find that underlying function f that would map an image to the label sets. So that was the idea, and I also told you how to do it at an abstract level, that you start by guessing what f is and then you refine your guess using the observations that you have made. Okay. At the end of the last session I told you that this approach is not feasible for all problems because it is very hard to get to the physics of the problem and try to discern the underlying function. Okay. The example that was given is that of a coin toss, where if you want to predict what the outcome of a coin toss is, given that you have made some observations, what observations one can make? You can make observations, physical observations such as the weight of the coin and the angle at which it would get tossed and what are the environment conditions, etc. Having those observations, predicting or rather finding out what the coin toss is going to, the outcome of the coin toss is going to be, is rather difficult because modeling the physics is hard. Now another example that could be appreciated is that of the image classification or the X-ray classification that we taught. It is more so difficult because what you are measuring is the amount of light that a surface reflects or rather observes or lets pass through it, and what you want to predict or learn a mapping to is an abstract synthetic concept such as diseased or not diseased. So now finding this mapping or relationship is not trivial starting from the physics of the problem. Now what is the solution for this is that lot of the machine learning engineers resorted to the statistical way of solving this problem, where instead of trying to solve the problem from first principles, from the physics of the problem, try to solve it statistically. So now what do you mean by trying to solve it statistically? That you make multiple observations and see if you can discern what the underlying function is via multiple observations that you have made. So this is at a very high level, broad level of what we would do in the probabilistic framework. Now we will concretize those ideas today. Okay, what do you mean to say that you make multiple observations, and what is the correspondence between the function learning and the probabilistic theory and statistics and so on, is what we are going to do today. See, this understanding is key to understanding the probabilistic framework of machine learning. So because I have seen oftentimes people miss this. right? So when they see that, oh, there is a distribution function that is appearing, it's very hard to relate it. See, when I say that you are estimating a function, I say that there is an image, there are labels, there is a function that relates the image to the label, and all you are trying to do is learn that function. The understanding is pretty neat. So if I say that there exists an underlying distribution that we are trying to estimate through divergence minimization, it's pretty hard to connect that, but that's precisely what's happening. So I'll spend some time in trying to bridge that gap between what this function approximation angle that we saw, which we have been studying from our high school days, and how does that relate to the statistical probabilistic ideas that we have studied in the first course of probability. So that is what I'm going to talk about. Okay. So probability theory, right? I'll just give you a 10-15 minutes quick introduction on what probability theory does. Okay. So we have to decide under uncertainties. So deciding under uncertainties, we wanted a framework, a mathematical framework to see. It's ironic and funny that despite the fact that you are using probability theory to model all this, finally the decisions are deterministic. See, a clinician cannot say to a patient that you are diseased with a probability of 60%. It's of no use. So decisions are to be deterministic, right? So however, the conditions that we start with are rather non-deterministic, okay, and we have to take decisions in a under an uncertain scenario. So that is why we need a mathematical tooling to handle that. So in fact, as I told the last time, the only thing that is rather not defined, very well defined in the entire probabilistic theoretical space is the notion of randomness. We start with something called a random experiment. So everything starts from something called a random experiment that is not well defined. So there is, we assume that when we start probability theory, we assume that we have an understanding of what a random experiment is, and we start by saying that this random experiment results in a few outcomes that are measurable. This is what we start with, right? In fact, it's very funny again to note that this is the farthest extent that we use the word random. So once we say that there is a random experiment and we have a few outcomes that are observed as a result of this random experiment, all randomness stops. Everything else is set theory and measure theory after that. Okay, as I said in the last class, there is nothing random about a random variable. It's a deterministic function. Okay, so we say that excuse me, we say that there exists an experiment which we call a random experiment, and there are outcomes of that random experiment, and that becomes a set. The outcomes, collection of all possible outcomes of an experiment, becomes a set, and we know how to deal with sets, right? Typical examples are, so if coin tossing is a random experiment, then the possible outcomes are two faces of the coin. In fact, you should know that it is completely up to a designer to define what the underlying random experiment is, right? When you toss a coin, okay, you say that my random experiment is tossing the coins 5 times, and this can be my random experiment. So remember that a random experiment is not something that's sacrosanct. I mean, given a problem, you can imagine what the underlying random experiment is. The moment you fix your random experiment and your outcomes, everything else follows from that. Okay, so coin toss is one random experiment, and you can see the outcomes head and tail as the set of possible outcomes, and rolling a die is another random experiment that we talk of, right, in probability theory, and the possible outcomes are different phases and so on. Now, because we are dealing everything from a probabilistic standpoint, everything that you see has to be now related to a random experiment. Remember this. So when we do machine learning, our starting point is a random experiment. There exists a random experiment, okay, whose outcome we are dealing with. Now, I will concretize these ideas using the example that I started with in the last class, which is taking an X-ray and assigning labels to it. Now what could be the random experiment there? The random experiment there is the entire process of somebody getting diseased and they going to a radiology center, somebody measuring them, somebody imaging them using the X-ray machine, and then printing that thing and finally uploading that on a computer, and this entire thing, right, and the clinician sitting and putting a label on top of it. This is your random experiment. Do you understand? Now every data point that you get, every single input set that you would get, right, in machine learning should be now seen from this angle, that there is an underlying random experiment. Suppose you are dealing with, let's say, natural language texts. So let's say that your task is that you are given a paragraph, and the task is to find out whether that paragraph has positive sentiment or negative sentiment. So that is one problem that, okay, let's make it a little more concrete. Spam filter. You want to say whether a given email is spam or not. Now what is the random experiment that's happening here? Somebody thinking that they have to draft a spam email and drafting a spam email and sending it, and somebody labeling it as a spam or not, because the idea of spam is very subjective, you see. All labels are subjective, that becomes a little philosophical, but we will come to that in a while. You now see why, how everything can be seen as a random experiment, right? A text is a random experiment, an image is a random, or rather an outcome of a random experiment, and so on. Can all of you see this? Any questions on this? Is very, very important, right? So every data point that we get, or let's say that you are looking at some measurements from the brain, right? And you want to predict something on that measurement, right? So that measurement that you get is an outcome of a random experiment. So what's the random experiment? Somebody having a brain and doing something, and you're conducting that experiment and making that measurement. See this? Now, the moment we have a random experiment, I said that is where the randomness in probability theory stops and set theory begins. The outcome of this random experiment is collected in a set, and this set is called sample space, denoted by, this is called sample space, which is set of all possible outcomes of a random experiment. Now don't ask me what randomness is, I don't know. Okay, we assume that there is a random experiment and some, it is giving rise to some outcomes, and we collect all of those outcomes in the set. That's it. Okay. I keep saying this, the biggest irony in computer science is that we have deterministic algorithms to generate random numbers. We have random number generators, right? Algorithms for random number generation, and they are deterministic algorithms. Right? Come again? Pseudo-random numbers. Yeah, that's why you say that they are pseudo-random numbers, but yeah, anyway, right? So we have sample space, and all of you understand what a sample space is, right? Now, once you have a set, see, finally remember our goal is to do predictions, and our goal is to find out whether that X-ray is diseased or not. Okay. Now, just by seeing the process of obtaining an X-ray as a random experiment or the outcome of a random experiment doesn't help. We have to move from here. Now, how do we do it? The moment we have a set, we can't do anything if we do not assign a measure on top of it. We need to measure. So, given a particular set, we need to assign a measure, a mathematical measure that would tell me that would correspond to the, I should not be saying that it's the length of the set. Okay, it corresponds to some notion. Okay, so I will not go into the measure theory. I assume that people have the idea of what a measure is. I can give you examples. Let's say that we are looking at the real numbers as the set. Okay, if you are looking at the real number, you all know that real number is a set, right? A set of real numbers. Now, if I take a subset of real numbers and if I have to compare two subsets of real numbers, how do I compare? I cannot compare unless I have the notion of measure or length. See, one of the measures that all of us know on the set of real numbers is the length measure. It's also called the Lebesgue measure. So given a set, see, let's say that we have a real set, right? Subset of real numbers which are like this. One is like this, the other is like this. These are two sets. Let's say that this is set A and this is set B. Okay. Now, if I ask you a question, which set is bigger? Can you answer? Which set is bigger? Any answers? You would say it's set B. Why? Huh? Because we have the notion of length measure, right? And we ascribe, we compare sets using measures. This is the Lebesgue length measure that you have, right? So the length of set A is less than that of length of set B is what we say under the Lebesgue measure that we have associated. Now, suppose you have sets in R squared, right? What sort of measures can we talk of? We talk of area measures, right? So any set that we have, if we have to compare sets and assign a way to quantify how big or large or something, see, it need not be big. The semantics that we associate with a measure is totally subjective, and it's dependent on the person, or rather the setting in which we assign the measure. But we have to assign a measure to do anything on top of the set. Okay. Now we know about length measure, right? If we go to R2, then we have the area. If we go to R3, then we have volumes, and if we go to RD, then we have the generalized Lebesgue measure, right, which is the d-dimensional integral volume and so on. So now we know how to compare the sets. Now, suppose we have subsets of sample space. Consider the subsets of sample space. So what do you mean by subsets of sample space? Now suppose, let's go back to our example of the X-ray. So if our sample space, what does our sample space contain? Our sample space contain the outcome of taking multiple X-rays, right? Many people are coming, and all of their X-rays are being taken, and we enumerate all of that in our sample space. And please note that this sample space is still not a real number or anything. So it is simply, see, in the coin toss example, the elements of our sample space is simply head or tail. It has no numerical notion yet. Similarly, this is very important. I will tell you why this is important in a while. So please note in your minds that the sample space is not numeric, may not be numeric. So it's a very abstract idea. So the idea of sample space is it contains all possible outcomes of an experiment. Now this outcome is, as I said, somebody having a disease, getting imaged, and this entire notion. So how do you quantify that? I have not come there yet. That's where we need the notion of random variables. Okay, push forward measures as they are called. We'll come to that in a while. So for now, you should appreciate the fact that the notion of sample space is independent of anything numeric. It's just that some experiment is being carried out, and we are enumerating the outcomes of the experiment in a set. That's it.
So, in the X-ray example, what are the elements in the sample space?
As I said, it is the question is what are the elements of sample space in the X-ray example. It can be anything. See, one way to construct the sample space is that somebody getting diseased, and they are coming, the entire imaging is happening, and they are being detected that they have disease. So this is one element. No, the question is how to quantify this. We'll come to that in a while. So sample space is rather abstract. It can be abstract. It need not be measurable. Not in the measurable sense of the measure theory. It need not be numeric. Let me say it that way, right? So that, see, as I said, the last class I said English is very fragile as a language. So that's why we need math as the other language. So now, see, sets by construction may not be numeric per se. Right? It's just collection of objects. Even if you study set theory, the definition of set is that it's collection of objects, and if you ask them what are objects, we assume that we know what objects are, and then we proceed from there, right? That's how it is. Okay. So now if you consider the subsets of sample spaces, Just like we could consider the subsets of real numbers and assign measures to it, the question is, can we assign a measure to the subsets of sample spaces? Is the question. Just like we have the length measure, the Lebesgue measure on subsets of real numbers, can we assign some set of a measure, the notion of the length of the set, is equivalent to the length of the set in the case of real subsets of real numbers? Can we assign a measure on top of the subsets of sample space? Does that question make sense? It makes sense, right? It need not be the length measure, by the way. It is not actually, right? It is some other measure. So can we assign? So please remember, please note that if you have a set, you can construct subsets of that set, and each of this, on each of the subset you can assign a measure on each of those subsets. Okay. So the question, so let's denote this by subsets of subspace. Let denote, capital F, denote the collection of all possible subsets okay. Question, or rather objective, is to assign a measure on F. See, I may sound a little hand wavy because this is not a course on measure theory. There's an entire course on measure theory where these notions are made more formal, but I am just giving you the intuitive idea of what this is. It very roughly take a set, construct the subsets of those sets, and try to assign a measure. Okay, there are properties of what a measure constitutes, right? For instance, the measure has to be non-negative, and it has to, if you take two sets, one is subset of the other. There are properties, just like you have properties of subspaces, you have properties of measures. Okay, which would, when would a function constitute a measure? There are a few properties that it should satisfy. Now the question is that, or rather the objective is to assign a measure on the subsets of sample space. Okay. Now one measure that we assign, which we work on, is what is called as the probability measure. Okay, probability measure is one such measure. Either you can say it probability or probability measure or anything. Okay, so it is denoted as P. Measure is a function, right? So it takes elements of F. What is F? Set of all subsets of the sample space, and assigns it to, particularly probability measure, assigns the elements of F to set of 0, 1. This is by construction. This is by definition, right? So this is how we assign a measure on top of the subsets of sample space. Now, there are a few properties that we ascribe to this. So what are the properties that we have on this probability measure? So let's look at the properties. See, this is very equivalent to the Lebesgue measure, the length measure. So if you want an analogy, always think of this as the length measure on subsets of real numbers. Okay. Properties of P. What are properties of P? You have studied all this, right? So one is, I will not enumerate all of this. So the measure, so if let's say that if A, B are two elements that are in F, first property is probability measure of A is you take any subset of any element in F, this probability measure always has this measure to be either 0 or greater than 0. So strictly non-negative, similar to the length measure. Okay. But the other thing is, this is upper bounded by 1, unlike the length measure. Okay. And what are the other properties? So this measure, the measure that is on the entire sample space is 1, the measure that is assigned on the null set is 0, and what else? If you take two sets A and B such that the intersection is null, then the measures add. Thanks. Right. So these are the properties of this particular measure that we have assigned. Okay. Now till now we have not interpreted this measure. This is still a mathematical construct, right? And now you can interpret this as the likelihood of this event. Okay. So don't ask me what likelihood is. Just like you don't ask me what length is. You understand what length is, right? So there is a measure that would assign a number to length. So now assuming that we all know what likelihood is, so there is, so and by the way the elements of f are also called events. Elements of f are called events. So every event which is a subset of the sample space is assigned a measure, and this measure is called the probability measure, and this which has these mathematical properties. Now if you want to assign a meaning to it, assign a meaning to it. In fact, all the machine learning runs even without you assigning a meaning to this measure. Right? The only time when you have to assign a meaning to this is when a doctor is actually have to use the algorithm that you have built and finally hand over a diagnosis to the patient saying that you are deceased or not deceased. Till that, you don't need to assign any meaning to this measure. You get it? See, that's the power of math. If you abstract out the ideas, right, you can work in the space of abstractions, and you can defer the meaning assignment to the very end. So I'll tell you one other philosophical observation that I have made over years. See, if you start seeing the world from a very abstract viewpoint, then cross-pollination across ideas is very, very easy. For instance, it's very easy for a probabilist or a mathematician to pick up machine learning. And see, that's why they say that physics is applied math, because precision and formalization and abstraction is very, very powerful. So if you start seeing, so in this case, this entire course is designed in such a way that you see data as the elements of the range space of random variables. And if you start seeing the data that way, then you don't care if you are working on images, or you are working on text, if you are working on a time series, if you are working on brain images, nothing. So I keep saying this always. I am a general machine learning scientist, generalist. To me, anything that you give are just vectors. What are these vectors? These vectors are the elements of the range space of the random variable that I am talking about. There is an underlying probability measure that I am trying to estimate using algorithms. That's the way I want to see the problem. So that's why I can handle images, I can handle text, I can handle whatever data that you want. That's the power of abstraction and generalization. So one needs to appreciate it. Anyway, so now that we have a measure on the subsets of the sample space, now we can, for our understanding, we can assign a measure. We can assign some meaning. We can say that this gives you the likelihood of the occurrence of particular event. Now, what do you mean by likelihood? Don't ask me. We assume that we all know what likelihood is, because it is bounded between 0 and 1. So if probability measure that is constructed, or probability measure of a subset of, or rather an event, is equal to 0.7. As a mathematician, or rather I would stop there, but if you want to assign a meaning to it, you say that there is 70% chance that this event would occur.
I think these meanings help us develop better intuitions about the underlying disease.
No problem. See, if it helps you to develop better intuitions, I am fine with it. But all I am saying is, all the piece of the maths will just go through even without assigning meanings. If you don't assign meanings, it will be helpful because in one problem it would mean something. In one other problem scenario it may mean something else. You have to assign meaning at the end to make it work, okay, whatever that means. But you don't have to restrict yourself in assigning meaning is all I am trying to say. See, just like the length Lebesgue measure need not correspond to, see, in fact I will tell you very interestingly, suppose you are constructing the area under some curve. That may correspond to different things in different contexts, right? You see what I am saying? See, area under the curve of acceleration is something else, area under the curve of some other measurement is something else and so on. But the underlying measure is the same. So similarly, look at probability as a measure on subsets of sample space. Now, you ascribe whatever meaning you want. But generally people see this as the likelihood. See, what happens is, when people start teaching or studying probability theory, they would approach that, I mean, they start by saying that, oh, there is some event and there is some likelihood of this happening and that's what probability is all about. I mean, that's a bad way to look at things. To me, it's a very neat mathematical construct where there is some set and you have subsets and we have defined a measure on top of it. That's it. Make sense? Right? Whatever meaning you want to ascribe, you ascribe it later. So, as I said, generally, probability measure is seen as the one that would give you the likelihood of occurrence of that event, whatever that means. Okay? So, this actually begs a very philosophical question, right? I talked about ignorance modeling in the last class. Now, tossing a coin, given that you are an omniscient, that you can determine the entire physics of the problem, you can deterministically predict what the outcome of the coin is. Because we cannot do it, we resort to all of this, right? So there is, I mean, again, this becomes too philosophical, right? There is nothing random about the world. So as I said, randomness is even not defined. You say that there is an experiment, some outcome is happening, enumerate all the outcomes, call it a set, define subsets on top of it, assign a measure, that's it. Okay, thank you.